Section 9.1, Correlation. We talk about correlation over in Unit 3, and basically it is the linear component in algebra dictating where a y is in relationship to x. It's basically the slope. In algebra, we have a perfect line. However, in the real world, when we're doing samples, we try to see if there's a pattern in that direction that can be described algebraically. You can see my three pictures here. I've got positive correlation up and to the right, and that's the same as positive slope. Negative correlation, the middle one, as y increases, x decreases, and vice versa. And then the third one on the very right, no correlation. There's no relation between y and x. The correlation coefficient is found with this formula here. This r equals n times the sigma xy minus sigma x times sigma y all over square root of n times sigma x squared minus sigma x squared times n times sigma y squared minus sigma y squared. This is the populating coefficient, and I'm going to show you a simpler way. In fact, I've created a calculator for you to use, but I want you to understand how we derive this information in the first place. Now, correlation goes from -1 to 1. A perfect positive correlation would be 1. A perfect negative correlation is -1. A positive 1 slope or -1 slope. And no correlation is a 0. Now I've used my formula here, and what I've done is I use Microsoft Excel to show this. This is based on the gross domestic product of, we've got, 10 countries here, and their relationship to CO2 emissions in millions of metric tons. And what I've done here is first I've summed up the GDP, which is 22.6, the sum of CO2 in metric tons, right here, that's my y, and I multiply my x times my y. 1.8 times 604.4 is 1087.9. Then I sum those up, the multiplication. Then my x squared, let's say 1.8 squared at the very top here, 1.8 squared is 3.2. And I summed all those individual squares up and I got 65.5. Finally, I squared my CO2 emissions. 604.4 squared is 365,299.4. Then I summed all those individual y squares up. Because that's what these formulas for. As you can see, here's my sum of xy, here's my sum of x, here's my sum of y, this is n, there's a number of samples here, here's n again, and here's n again. And then it's x squared, which is right here, 65.5, minus the x, which is 22.9, squared. So 10 times 65.5 minus 22.9 gives us 130.49. Same thing with the y. N times y squared, which is 33,120,000.9 times or minus the y, which is 5129 squared. Those answers are these incredible sets of numbers here. But in the end, when I divide it up, I get a correlation coefficient of 0.874. Now remember, 1 is a perfect positive correlation, -1 is a perfect negative correlation, 0 is no correlation. So this is close to a positive correlation by 0.874. It's almost a perfect correlation. In other words, the higher the GDP, in this case, the higher the CO2 emissions. Now, here's another one. Calculate the correlation coefficient, the number of years out of school and any contribution into retirement. And I've got 7 individuals here. And on X, I've got number of years out of school, 1 year, 10 years, 5 years, 15, 3, 24, and 30. And then in $1,000, their annual contributions. The 12.5 is 12,500. My sum of X is 88. My sum of Y is 56.7. Then multiply X times the Y. And I sum that up for My sum of xy is 435.6. Sum of x squared, well, 1 squared is 1. 10 squared is 100. So those up, I got 1836, and the sum of y squared is 587.1 when I multiply y by itself, and I sum all those up. And again, I got all my answers right here in these summations here in Excel. And then I just plug it in. You can see my n is 7. I got that in 3 spots here. I got my individual summations. There's 7 there. 436.5, which is the xy. Then it is sum of x times sum of y, 88.56.7. In my denominator, I've got my number of samples. Then I've got my x squared, which is 1836, minus my x, 88 squared, and then 587.1, which is my y squared. I'm sorry, let's see here. Yeah, no, actually, yeah, 587.1 minus 56.7 was my y squared. I get negative 1940.4 in the numerator, negative 1.1940.4. And in the denominator, I got square root of 5108 times square root of 891.84. I get negative 0.908. And this is close to negative 1. So this is a strong negative correlation. In other words, the longer someone's out of school, the lower their contribution to their retirement. Now, we determined how to see if it's a positive or negative correlation and how strong it is, but we can determine statistically how significant it is. What I have here to the right is the Pearson Correlation coefficient. This allows us to determine if it is statistically significant. And we use an absolute value. Our last page, we got a negative 0.908, a strong negative correlation, but let's use the absolute value. It works either way. And we've got a 0.908, and there were 7 samples here. So my n is 7, and my alpha was 0.05, not 0.05, 0.01. And that means if it is equal to or greater than this number here, it's a strong correlation. We got 0.908. This is 0.875. 0.908 is greater than 0.875, so it is significant. So what I've got here is pairs of data of Old Faithful, the Yellowstone National Park, roughly erupts every hour on the hour, and so it's called Old Faithful. And my X column is how long it erupts in minutes, 1.8 minutes, 1.82 minutes, 1.9 minutes. And then the time, my Y component, is how long between eruptions. We want to see if there is a statistical significance and a correlation between how long it erupts and time between eruptions. Now my X, sum of X, 82.52, my sum of Y, 1872. X times Y, the sum is 6526.16. I've got also my sum of X squared, 300.19, sum of Y squared, 144,698. And I'm not going to read all these numbers for you. You can see where I put them all in here into the formula. These are all numbers, and my number of samples is 25. I get a 0.979. And when I looked at the table on the previous page, alpha 0.05, P for 25 is 0.396. 0.975 is greater than 0.396 as the absolute value. So there is a strong correlation between how long it erupts and time between eruptions. Now, we can also do hypothesis testing to see if there is level of significance, greater than or less than, greater than equal to, less than equal to, or if there is a correlation or no significant correlation by looking at 2 different samples. And once we have the R, which we figured out in the previous few pages, what we then do is we can find our T critical at R over 1 minus R squared over N minus 2 number of samples minus 2, square root of all that. So what I've got here is we're looking at the GDP of 10 countries and in relationship to their millions of metric tons of CO2 that you emit. And if you remember, when we calculate all this, we got our correlation of 0.874. So we want to figure out, is there our hypothesis testing to see if it's significant at 0.05? Let's figure out our t first, our t critical. Well, r is 0.874 in the numerator over the square root of 1 minus 0.874 squared over n minus 2, which is 10 minus 2, which is 8. And that's 0.874 over the square root of 0.0295155. Square root of that's 0.1718. 0.874 0.718 is 5.087. So that is way over here. And if we're looking at critical points here, our alpha is 0.05, so that means it's 95% in the middle, which is 0.025 on both sides. So let's look at this here. Now, when we read this, when we're looking at correlation, we subtract 2 because we're getting 2 different groups of data, the x and the y. So for the degrees of freedom, instead of n minus 1, it's n minus 2. So I've got 10 samples here, which means 8 degrees of freedom. 10 minus 2 is 8. So it's two-tailed because we want to see if it's equal or not equal. So I'll go over here, 2 tails, and it is 8 degrees of freedom, which is right here. And then it is at alpha at 0.05 for 2 tails, which is right here. Now, alpha 0.05 for 2 tails is going to be 2.306. So it's 2.306 as I've written it here, and negative 2.306 since it's two-tailed. And our t at 5.08 is on the outside. So I would reject the null hypothesis and say there is significant correlation there. Now, on this one here, I've got the data for 30 major league teams based on the salaries per year in total for all the players and the average attendance. So I know, is there a correlation between salaries and attendance? I used Excel. This is why I like using Excel. It's easy to sum all this up. Sum of x, I got my sum of y, my sum of xy, sum of x squared, sum of y squared. And when I figured out my r, I got an r, and I put all these numbers in. Do the calculation, 0.775. Now this is 30 samples, so it'd actually be 28 degrees of freedom, 30 minus 2. So here's 28 degrees of freedom, and alpha is at 0.01. So it'd be 0.4. Let me see. It'd be at 0.4. I'm sorry, it's not minus 3. It's 30. That we're not doing the hypothesis testing yet. It is 30 samples at 0.01, 0.463. And we got an R of 0.775. The absolute value of 0.775 is greater than 0.463. So there's a strong significance correlation. It is a very strong positive correlation. Now we want to determine, do we reject or fail to reject whether there's significant correlation here? And all I'm going to do, as before, to find my T critical, is 0.775, which is my R I found, divided by square root of 1 minus 0.775 squared over 30 minus 2. This is with a subtract 2, which is 28. 1 minus 0.775 squared over 28 is 0.01426. Square root of that is 0.11949, which is 775. 0.775 over 0.11942, which is 6.48, which is way out here. Now, I want to know if their significance is equal or not equal, so it's two-tailed. and there's no significant correlation in terms of hypothesis testing, they'd be within these two um, ranges here for the T criticals. And the T critical here, which is 30 samples minus 2, 28 degrees of freedom, and here's 28 degrees of freedom, it's two-tailed, and at 0.01, here's two tails at 0.01, and this would give us 28, two tails, 2.763. So it'd be plus or minus 2.763. Anything outside of these, we'd fail to reject. We reject. Anything outside of these, we fail to reject. And T at 6.48, we would definitely fail to reject. Way outside of point T at 2.763. So there is a significant difference. Now, what I've done here is those are a lot of calculations, and I've tried to make it very simple for you. I've added, you can see it in this module, correlation regression calculator. I've created an Excel sheet, and there's two places where you input the numbers. And I've highlighted those in yellow here. I've locked everything else down so you really can't mess with it, but it calculates everything for you. You got to put in the numbers, and this is for those baseball teams. My X 78.4, I put in 25,138. It calculates my X times Y, my X squared, my Y squared. Sums it up right here. You can see this is actually right below the sheet, and this is in Excel. It gives you the sum of X, it gives you the sum of Y, the sum of XY, the X squared sum of, the sum of Y squared, and actually does the calculation for you too. So you don't have, I'm just showing you what these numbers are, but it gives you the answer right here. 0.7747, which is 0.775, which is the answer we got. Again, all you have to do is input the numbers here and make sure you put the number of samples here. In this case, it was 30, and everything else will calculate out for you. This makes it a lot easier. It's more important that you understand what correlation is. I'm not worried about you doing the detailed calculations, because in the real world, you would have something like this to do it with.